Hi, welcome to Module 5, Part 2. And we left off on conditionally stable, and we said that conditional instability occurs when I have parts of time where my environmental lapse rate is warmer than my adiabatic lapse rate locations. And so I have spots in the atmosphere where the air parcel is warmer than, and then other parts where the air parcel, the air that's rising or lifting, is cooler than the environmental surrounding air. Factors that affect environmental lapse rate are dependent on a lot of things. It can be environmental lapse rate, the rate at which the atmosphere is cooling as it increases in altitude, changes day by day, and it's based on different things. So some parts of the year, the rate of cooling, so the difference between this point in the atmosphere and the point 100 meters up, can be based on heating and cooling in the troposphere. This is all troposphere. It can be based on advection or cold or warm air at different levels, which can create trapping. And this trapping process is called an advection of air mass. And we'll talk a bit about environmental lapse rate and advections of air masses in just a few slides. So here we go. Heating and cooling in lower atmosphere. There's some variation in lapse rate, and some of it can even change based on time of day. For example, the cooling variation that I can expect in the latter parts or afternoon of the day tends to be more extreme. So the cooling off is more extreme from altitude change to altitude change than in early parts of the day. In early parts of the day, the change in temperature is less extreme as I go up in the atmosphere. And this is based on place to place. As I mentioned, though, in our location in the New York region, it's about 6.4, but it varies anywhere from about 5 degrees Celsius up to about 8 degrees Celsius at any given point in time of year, time of day, and location on the latitude on my environmental lapse rate. Advection is when I see a reversal in my activity, so cold and warm air masses at different levels. So I can expect a warm air mass at the surface and a cooled air mass up above. Because I have a warm air mass at the surface and a cool air mass up above, what I can see is a reversal in wind directionality. So I will see my natural warm air continue to move from its standard high to low pressure, but my cold air might make a flip in its location of travel. And this has to do with the properties of thermodynamics that basically says that I will go from hot source towards cold sink. And that's the natural direction. So cold sinks are being forced out of their location by hot sources of air mass. Advection air mass, once again, talking about lapse rate, different times of day, how the air mass might move versus temperature and U. If the air in the air parcel happens to be cooler than the air around it, the environmental lapse rate air, then I will expect no rise to occur. This is considered extremely stable because I have no vertical lift. And when I'm in times of extreme stability, I don't see a lot of airflow to blow out problems. So think of places like San Francisco when the fog sets in. There are points in time where they experience extreme stability, where instead of the daily morning fog setting in and then the sun coming up and over the horizon and warming things up, and the humidity level going down as the air molecules get warmer, making more space, right? Reviewing things we've already learned from the previous chapter, making more space. Sometimes I have extreme stability and the variation in the sun's temperatures does not warm up the atmosphere enough to dehumidify the air around it, and therefore it stays foggy and it sets in and it gets stuck in those conditions. Just some different examples of extreme stability so that I'm having no air motion. So I have like air parcels stuck in variable locations because they're not necessarily warmer or cooler. there is this sort of natural divide, and I'll see one air parcel at the surface, but it's not able to break up past a certain altitude because I have another air parcel going in the other direction. So I have one coming at the camera like this and another one zooping off the top in this direction, right? So I'm not seeing any mixing. There's no vertical mix of my air, creating extreme stability. So the air down here is kind of stuck in that location. The air up here is moving away. Cloud types. Now, there's a couple slides here that explain cloud types, but I don't like that they're not divided up into their categories. And so I'm going to flick over to a different PowerPoint that I'm providing for you here that just kind of categorizes everything cleanly and then goes through some of my pictures that I've taken of clouds because, well, you know, I like weather. So welcome to cloud forms. And I'm going to give you some images of strange and unusual clouds at the end. But before I get into the strange and unusual, I'd like to give you the main four that I can put into categories. And they're very easily divided up into high clouds, ones in the upper parts of the atmosphere, middle clouds, low clouds, and then vertical clouds, clouds that start in what I consider the low cloud region and move all the way up vertical to the high cloud region. You can also see that there's some key terms that stick with it. And so if I see the word CIR, C-I-R, in my cloud name, especially at the front of my cloud name, CIR means upper altitude, so high altitude clouds. These are stuff at the top of just my troposphere. None of this is going on in the stratosphere. So this is just at the top of my troposphere. Then I can see middle, alto. You think of music, right? The altos are the middle range of sound. And so alto, alto stratus, and alto cumulus clouds. And then low have the word strata in it. So I can see stratus, stratocumulus, nimbostratus, right? And vertical, you can think of cumulus nimbus, thunderstorm clouds, and cumulus clouds, the big puffy white ones that look like cotton balls in the sky. So high altitude clouds have an elevation about 20,000 feet or higher. So that's kind of their minimum. And once again, they come in cirrus, cirrocumulus, and cirrostratus. Cirrus clouds, here we go, cirrus clouds are named after wisp or wisp of curl. And these are kind of those altitude, high altitude wispy things. You can also sometimes check out the jet stream based on the directionality of the cirrus clouds because they're getting pulled apart by very high altitude winds moving in natural wind currents. And while we haven't covered winds or jet streams yet, this is one of the ways that you can actually check out the motion of the uppermost parts of the atmosphere, or not atmosphere, the uppermost parts of our troposphere, looking up and just noticing which direction the cirrus clouds are being pulled apart or pulled away in. Cirrocumulus, cumulus once again is the puffy clouds. So when I put the word cirrocumulus, I'm saying high altitude puffy clouds. And so these high altitude puffy clouds will blanket the sky. They can block out quite a bit of sunlight, so they can make a bit of a gray day when you see them. And another cool thing is when you have a sunset, if the sunlight and the angle of the horizon can get down below the cirrocumulus clouds so that some of that light can come through, it'll actually reflect back. It'll create a refraction effect on the cirrocumulus clouds, and it does what's called the mackerel sky effect. It looks like fish scales shining in the sky, which is kind of a neat effect and something that's exclusive to cirrocumulus clouds. They have to be that high altitude cloud, and they have to be that puffy to get that scaly effect. Cirrostratus clouds are cirro and stratus. Stratus means sheet. So I'm talking about a sheet cloud in the very uppermost parts of the atmosphere. If I see a cirrostratus cloud, if I'm having one of those weird gray days, and it's just that thin layer over the sky, and if I look up and I can see the sun and I can see that halo around the sun or halo around the moon as I look up, don't normally look at the sun, but as I look up, if I see that, I can actually tell you that it's going to rain within 12 to 24 hours if those cirrostratus clouds do not clear out in that time. So they're an easy indicator of storm conditions. You'll also look like a genius as you tell people the weather, but it's such an easy indicator that you're going to get the precipitation. It may not be heavy precipitation. It might be a light all-day rainy drizzle day, precipitation. That's actually the more common type. It'll be that light, all-day rainy drizzle day, but not immediately, 12 to 24 hours later. So middle altitude clouds are anywhere from 6,500